Hi everyone. In this video we're going to work on pushing arrows for certain elementary steps as well as determining the frontier molecular orbitals of these elementary steps. And so we'll be working on problem C here, where we're looking at the reaction between a benzene ring and this nitronium ion here. So in this type of arrow pushing we have an electrophile addition. And remember that electrophile addition is going to involve taking electrons from a pi bond, attacking the electrophile, so in this case the pi bond is acting as a nucleophile. Nitrogen here, though, is going to have one too many bonds to it in this case. So already it's got 4 when it really would prefer 3. But if we were to add that 5th bond, this would be violating the octet rule. So what we're going to have to do is we're going to have to break one of these nitrogen-oxygen pi bonds in order for this operation to work successfully. In terms of products, this is going to give us the following cation. So our carbon is going to be connected to the nitrogen electrophile. However, this carbon, which was originally making 4 bonds, because of the pi bond over here, is now only making 3, and because of that, that is going to have a positive charge. One way we can check whether this reaction has its arrows pushed correctly is that the net charge from the reactants over here should equal the net charge of our products. So overall we have a net positive charge over here, and while we have 2 positives and 1 negative over here, these sum to a net positive 1 charge. Okay, so that's a little bit of a review from last term. Where this is a little bit different is I want you to determine the frontier molecular orbitals that are overlapping in order for this elementary step to happen. In this case, these are the highest occupied molecular orbital and the lowest unoccupied molecular orbital. In the reactions that we've discussed so far, the highest occupied molecular orbital is going to house the electrons that are used as the nucleophile. So in this case, the benzene is acting as our nucleophile here. And more specifically, it's the electrons in the pi bond of the benzene that are reacting. And so, while this is a slight oversimplification, our highest occupied molecular orbital here is going to be the pi bond of the benzene ring. The lowest unoccupied molecular orbital, or LUMO, is a little bit more difficult to discern. But essentially, this is the orbital on the electrophile which is going to accept the electrons from the nucleophile. And so in our ion here, you can see that we don't have any orbitals which are simply empty from an atomic perspective. So we're going to have to look to molecular orbital theory to find our lowest unoccupied molecular orbital. An easy way to do this is to look at the bonds that are broken going from reactants to products. And so you can see, yeah, we're breaking our pi bond over here, but that's because we're using it as a nucleophile. Over here, though, you can see we are breaking a pi bond between nitrogen and oxygen as a consequence of nitrogen there just having too many bonds. Remember that to break a bond, one way to do this is to occupy an anti-bonding orbital, which is oftentimes empty. And that's what winds up happening here. So our lowest unoccupied molecular orbital actually winds up being the nitrogen-oxygen pi star orbital of our electrophile. And this winds up making sense because, first of all, we know that a nitrogen-oxygen pi bond, in this case pi star, is going to have orbitals that look like this. And so we know we need to form a bond between nitrogen and carbon, so we've got lobes here that allow us to do that. Additionally, as soon as we put electrons in this bond, this cancels out the bonding pi orbital between oxygen and nitrogen, essentially breaking the bond, which is exactly what we want to do from our arrow pushing to our products. Hopefully this is helpful. I'll be making a couple more videos about this in the near future. See you soon.